Hello, and welcome to today's presentation on iterated integrals. Alright, iterated integrals, also called multiple integrals. If you recall, we have already seen how to take the partial derivative of a function. When we do this, we take the derivative with respect to one variable, and any other variable is treated as if it's a constant. So, for an example here, if we have f of x comma y is equal to 5x squared minus 4xy cubed plus 7y. If we take the derivative of this with respect to x, then we get the derivative with respect to x is going to equal 10x minus 4y cubed. Now what we're going to do is we're going to apply this concept to integration. So let's take a look at the following integral. So we have the integral of 6xy squared dx. So what this is saying is we're wanting to integrate the function 6xy squared with respect to the variable x. In other words, the integration rules are going to apply to x, and we're going to treat y as if it is a constant. So doing that, adding 1 to the exponent on x and then dividing by the new exponent, that will end up giving us 3x squared y squared plus c. So if you remember from previous calculus courses, we had to do that plus c. But this is not exactly correct. If we have a term that has only the variable y in it and we take the derivative with respect to x, that term becomes 0. We saw that in example 1. So that means the c in this antiderivative might have the variable y in it. So correcting our notation, we're going to have something that looks like this. The antiderivative, or the integral of 6xy squared dx, that's going to be 3x squared y squared plus c of y. So that says that the integral of 6xy squared is going to be 3x squared y squared and then plus some algebraic expression that will have at most one variable in it, and that's going to be y. And we're going to use the notation cy for that. Now, for the rest of this lesson, we are going to be doing definite integrals, and we're not going to be worried about adding this plus cy at the end of it. So let's take a look at a definite integral. So here we have the following definite integral. We have the integral from 0 to 3y of 6xy squared dx. So we take the antiderivative with respect to x. That gives me 3x squared y squared, and then we have to evaluate this from 0 to 3y. So plugging in our endpoints, that ends up giving me 3 times parentheses 3y squared, and then times another y squared, and then minus 3 times 0 squared times y squared, which ends up giving us a 27y to the fourth. So we took the antiderivative of that with respect to x, and then we plugged in those endpoints. Now let's consider the following. This is a double integral, sometimes called an iterated integral. So what we have here is we want to do the integral from 1 to 3, the integral from 0 to 4 of 6xy squared dy dx. So the way these iterated integrals work, the way these double integrals work, is we're going to do the inside part first and then the outside. So when you take a look at it, this outer integral that goes from 1 to 3, that matches up with my x, and this inner integral from 0 to 4, that matches with my y. And in some ways, I actually kind of see these integral symbols and these dy's as sort of a left parentheses and a right parentheses. So we effectively have one grouping inside of a second grouping. So here I kind of wrote it with some brackets so that you can actually see it better. So evaluating the inside integral first. So integrating my 6xy squared with respect to y. That's going to give me a 2xy cubed, and then we want to evaluate this from 0 to 4. So plugging in those endpoints, that'll give me a 2x times 4 to the third minus a 2x times 0 to the third, which gives me 128 times x. Now we want to integrate this thing with respect to x. So integrating this with respect to x, this is going to give us 64x squared, and we're going to go from 1 to 3. So that gives me 64 times 3 squared minus 64 times 1 squared, which ends up giving me 512. So we have calculated our first iterated integral. So this lesson is going to can be extended to 3 variables, and we're going to see that in a later lesson. But effectively what happens is we just do one more iteration of the integration. It's not really anything different. So let's take a look at this problem again, because I want to point some stuff out. So when we take a look at this, the endpoints on the y go from 0 to 4. The endpoints on the x go from 1 to 3. So when we take a look at the endpoints for x and the endpoints for y, this describes a region on your xy plane. So the iterated, the double integral, what we're actually doing is we're integrating across some area on a plane. So when we calculate an integral, here's another integral that I have. So this is an integral where x is going from 1 to 3 and y goes from 0 up to x. So we're going to be integrating over some region on the xy plane. So what I'm going to take a look at here is we're actually going to try to find out what region we're actually taking a look at. So when you take a look at this innermost one, we're going from y goes from 0 on the bottom up to the equation y equal to x on the top. And I have graphed that here. So that gives me this sort of triangular shaped region in the first quadrant. Goes from 0 on the bottom up to this line y equal to x. Now when we take a look at the endpoints for x, x goes from 1 to 3. So we're going to have a left boundary of 1 and a right boundary of 3. So that describes the following region. So anytime you're looking at a double integral, an iterated integral, you're basically integrating over some region in the xy plane. Now, some notation that you will see is instead of writing the endpoints on that integration, they might just say the double integral over some region R of our function, and then over here they would say dA, where A is representing the area. We're integrating across the area of that particular region, and that dA basically represents the dx and the dy, whichever order you want to put it in. Now, in terms of a meaning, if our function describes some property over that region, so if this function here, 6y squared, if that referred to the density of some object that has this shape, then if I integrate across that area, and this is the density, then we've just figured out the mass of the object. Or if this right here represented the height above that area in a third dimension, then when we do the double integral, we've actually calculated a volume. So we can actually use these double integrals to calculate things like mass, and we can also use it to calculate things like volume. Now, when we don't have a function inside of our double integral, we're integrating across some region, then this right here is going to calculate to the area of that region. So the calculus version to find the area of a region is going to be this double integral, where R represents that region, and you're integrating across that area. Now, as long as you keep that region the same, you can switch the order of integration. So for that first example, I had the integral from 1 to 3, those are the endpoints on x, and then the integral from 0 to 4, those are the endpoints for y. So I can reverse the order of integration 2, the integral from 0 to 4, which is still the same endpoints on the y, the integral from 1 to 3, which is the same endpoints on the x. So I can switch the order of integration and it will give me the exact same result. And here I actually went through to show you that it calculates the exact same result. So integrating with respect to x first, that gives me 3x squared y, going from 1 to 3. So plugging those in, I get 3 times 3 squared times y squared minus 3 times 1 squared times y squared, which will give me a 24y squared. And then we have to integrate this with respect to y. So that ends up giving me 8y cubed going from 0 to 4. When I plug in my endpoints, that gives me 8 times 4 cubed minus 8 times 0 cubed, which gives me 512. So this area was a nice rectangle. And if you have a nice rectangle, it's easy to change the order of integration. But let's say we have something that's not a nice rectangle, where x goes from 0 to 6, and my y goes from 0 up to some function of x. 0 less than or equal to y, less than or equal to 2x. Well, when I take a look at that region is going to look like this. So y went from y equal to 0 up to this line, y equal to x, and then x, the left bound, started at 0, and it went to this right bound, which is at 6. So let's change the order of my integration. So if I change the order of my integration, the left edge is going to be this slanted line. I'm going to go from this left edge to this right edge. So, got to find the formula for that left edge. So the left edge is y equal to 2x. If I solve that for x, that gives me x is equal to 1/2 y. So this line, y equal to 2x, is the same thing as saying x is equal to 1/2 y. So I can describe 1/2 y as a left edge, and then my right edge is still going to be 6. So here's my left edge, x is equal to 1/2 y, and my right edge is x equal to 6. So now let's take a look at the bottom. The bottom is going to go from y equal to 0, and then it goes up until I hit this particular cutoff point along the y's, which happens to be y equal to 12. How did I get y equal to 12? Well, I had y is equal to 2x, so when I plug 6 in for x, that gives me y equal to 12. So our region is described as x goes from 0 to y over 2, left edge to right edge, and then my y goes from a bottom edge of 0 up to a top edge of 12. So if I change my order of integration, that ends up giving me the following. I'm going from 0 to 12 along the y. I'm going from 0 to y over 2 along the x. Now, notice that the very last interval that we're going to be integrating across, notice those are numbers, 0 and 12. They're not algebraic expressions. This is very important if you want to actually calculate a numerical answer. So the exercises that you're going to see, you're going to see that they're going to be having that last pair always being numbers. So that's why I wrote this as 0 being the bottom, 12 being the top. If I had written anything else here, then I would not be able to calculate this to a value. Alright, thank you for watching this presentation, and I will see everybody next time.